We started the experiment by using a 55-gallon drum as our firing platform and leveling it by placing rocks under it until it was balanced. We checked the balance by using a level. Then we set up a plastic sheet as our target since we'd be able to see where the projectile impacts. We measured the distance from the edge of the barrel to the target. We had to subtract 48 inches from this number since the barrel of the cannon extended 4 feet past the lip of the drum. Then we used a laser placed on the level to find a point at the same height as the top of the drum. Since the ground was not level, we couldn't just use measuring tape. The cannon was then loaded and fired. Then we had to convert our units from imperial to metric. The distance from the muzzle to the target was 226 inches, which converts to 5.76 meters. The distance the projectile dropped was 4.5 inches, which converts to 0.1143 meters. Once converted, the calculations for kinetic energy can be done.
So first we're going to write out our variables. We have the change in position on the x-axis, which is 5.76 meters. And then we have our change in position on the y-axis, which is 0.1143 meters. Then we're going to be solving for our velocity and for our time. And then for our acceleration on the x-axis, it's going to be 0. And on the y-axis, it's going to be negative 9.8 meters a second square, or g. Alright, now we can start solving it. We're going to use the second kinematics equation, at least part of it. Its position equals 1/2 acceleration times time squared. So now we're going to substitute in for that. And we're solving for this on the y-axis. So we're going to substitute in 0.1143 equals 1/2 times negative 9.8. And then we're going to solve for time. So now we're going to multiply the 1/2 by the 9.8, and we're going to get negative 4.9 times t squared. And then we're going to move that negative 4.9 over to the other side. And when we move that over, we're just going to drop the negative, because when we go to do a square root, when we take the time squared, you can't square root a negative. So we get root 0.0233 equals time. And that comes out to 0.1527 seconds. And we're just going to write that over with our variables since it's solved. And then for the next step, we're going to use that same equation, but a different part of it. So we have position on the x-axis this time equals velocity initial times time. So we have 5.76 equals our velocity initial times our time, which is 0.1527 seconds. So then we can just divide by our time and come out to 37.72 meters a second as our initial velocity. Now we can use this to solve for our total kinetic energy. So we're just going to erase this. And write that over with our variables. So now first we need to solve for the mass of it. So we're going to do volume of a cylinder, which is volume equals pi r squared times height. And now we're going to substitute in for that. The radius being 0.0254 meters, that is. and then multiply that by our height. Which is 0.1524 meters. So when we solve for that, we get 3.089 e to the negative 4 meters. And then we can solve for the mass by doing volume times density of the wood, which is poplar, equals the mass, and the density of the wood is about 420 cubic meters per kilogram. Or kilograms per cubic meter, excuse me. And then we're just going to multiply those together. Then we're going to get 0.1297 kilograms as our mass. And then for the kinetic energy, we can solve that by doing 1/2 mv squared. And then we substitute in our values for mass and velocity. And then we can multiply all those together. Then we get a final answer of 92.268 joules.
The largest source of error was that we were not able to measure the velocity of the projectile at the muzzle, and instead we had to rely on the average velocity over distance. Because of this, it can be assumed that the actual muzzle energy of the cannon is somewhere in the neighborhood of 100 joules. Another source of error related to being unable to measure the velocity at the muzzle is drag. Although the cross-sectional area of the projectile is relatively small, drag should still be accounted for if you're trying to make an accurate calculation. The accuracy of the level used to level the 55-gallon drum is another possible error, which may have inadvertently introduced some unwanted velocity components on the Y or Z axis. Along with the accuracy of the level, another variable is whether or not the cannon was held flat relative to the top of the drum, which, since we did not have a mounting device, is a possibility.